So anyway, honestly, chem students, I'll tell you what the AP folks demand of them in terms of chemistry is that you drew all the water molecules in a polar state. We have one side's positive, one side's negative. And the positive negative is merely because of the shape of the water molecule. Okay, we have plenty of molecules that have positives and negatives that are not polar. Carbon dioxide, the stuff we breathe out, is a non-polar molecule, and it's not polar because it has the two oxygens in CO2 are exactly on the opposite side of the carbon. And so there's an oxygen, I always use my head as the carbon. And there's an oxygen here, and the carbon's in the middle, but they're exactly on opposite sides, so neither side is winning the negative tug of war, if you will. The oxygens are negative, and the carbon is positive. My head always ends up being positive somehow. But in water, the hydrogens are positive, and they're up top here. And so the negative is concentrated offset, and one side is positive and one side is negative, and in water my head ends up being negative. If you want to, just as a little aside note, if you ever want to have your kids be able to see that fact that water is indeed a polar molecule, it's really easy to do if you have one of these squirt bottles. You ever taken a balloon, you scrub it on your head and it'll stick on the wall? So if you do that and you hold the balloon here and you make a small stream of water, it'll evaporate, the water will curve towards the balloon. And it shows the polar nature of water real quick. As long as they know, it helps to pull out magnets, negative and positives attract and that kind of thing. Okay. Then they can argue about is the balloon negative and the water positive, or vice versa.
Do that like with a comb,
you can do it with a comb and
to the faucet, and it'll pull
yep.
like a stream of water.
You certainly can. Okay, yeah, and it'll pull that towards it. It's a real quick way to show the polarity of water. Okay, and it's that polar nature of water that makes it what we call the universal solvent. It's a liquid at room temperature. It dissolves because it's a molecular compound. It tends to dissolve pretty molecular dissolve things that are polar that split up like you did yours. If you look at, for example, that drawing over there, the AP folks will love this for a drawing of the water solution. As a matter of fact, last year they changed the test on it, and one of the questions was draw a solution of water. I mean, a lot of people think that's a really simple question, but it really delves into a lot of understanding about solutions. In that the sodium and the chlorine, they separate from one another, and they can't reattach because of what's surrounding them, the water molecules. Now, the AP folks insist that the negative oxygen is touching or attracted to the positive sodium, and the positive hydrogens are attracted to the negative chlorine. And they actually set down and say chlorine atom, or for each sodium and chlorine, there has to be at least 3 waters kind of surrounding it to show that the water actually surrounds it in some way. Okay? And so I see that in a lot of drawings, in a lot of places. As a matter of fact, this group over here, they actually showed the solvation process itself, starting from pure water to sodium and chlorine in the solid state, where they're in a regular crystalline pattern. Okay? And then as the water comes through, it attracts to the positive ions and the negative ions separately. Okay? Anybody know science terms? What do they call that process? When it disassociation, but the actual process of the water dissolving the salt, or the salt dissolving water, they call it. It starts with an S. Solution is the final product. They call it solvation. Okay, solvation. Okay, that's a huge term actually in the biotech industry. There's a solvation step when they do PCR, which is polymerase chain reaction, how they make DNA and replicate it. There's this big solvation step where the molecule expands and then it contracts due to the solvation forces. That's not about water and salt. But as we do this process, we have those sodium ions and the chlorine ions. Now, a couple of critiques. What do you think is larger? Tiny little water with hydrogen and oxygen. Hydrogen is the smallest atom. Oxygen is atomic number 8, not too terribly large. Or chlorine, atomic number 17, or sodium, atomic number 11. Which ones what do you think is larger? An H2O molecule or a sodium and a chlorine? Okay, and that's usually where things go south for my students too. Sodium and chlorine are actually smaller than the water molecule itself. Okay, so that leads to, even in our best filter over there, would we remove salt? When no. Now we solid salt crystals. Whether if we have too much salt to dissolve, you can't continue to dissolve salt, right? Eventually. Water in the sodium or the water in the chlorine. So it'll remove the solids, but even the best filter, best filter, you guys are getting some color through, aren't you? Okay, so your filter does have large pores to let the red through, right? Okay, so a good science term, if the first person to hand me a little sheet of paper that says, what is the attraction? They call that when that red stuff attaches to the filter molecules. Okay, there's an actual term for that. When the red molecules physically or chemically attract to that thing and attach to it, and that's why it's not coming through the filter until finally it can't do that anymore. It does saturate the filter, you're right, but the actual term for what it's doing is what we're looking for. And if we don't get it, we'll give it away with something else. Doesn't really matter. I think it's $1.90 or some crazy amount of money. This is true. This is true. It's like $2 is $2, man. It's 200 pennies. It's following me. Okay. So what we're really trying to get at here is yesterday and this morning certainly showed you can get rid of solids pretty darn easily and quickly and pretty efficiently. We did a pretty good job here. Notice that at every wastewater treatment plant, the first step is just let the water sit for a while. What? It's because sedimentation is huge. You don't want to filter all this. This is a disaster. Okay. I don't know if you remember your high school chemistry classes, but almost every lab where they have to filter, it almost conveniently ends where, we ran out of time today. We'll filter tomorrow. I do that with my classes all the time, and you can probably guess why. Yeah, it settles. And then what do the kids do to screw it up? Yep, they stir it. Sure enough, they stir it. Okay? And we go through one lab like that, where they'll stir it, and then we watch them filter. And filtering that with a, even if you have like a starch in there, which is a large molecule, it'll take days. Sometimes they won't filter at all. Okay, you'll make a little lake bed for it, and it just sits. And so then they learn, like, don't stir it, unless that's part of the directions. Okay. Sometimes you want to stir it because you actually want to not save the water; you want to save the filtrate, or the solid. But not usually. But the thing is, most of your experience is how do we get the water out, or how do we get the salt out of the water, or in some cases, it is correct to say, how do we get the water out of the salt? Okay, and the salt. I'd like to kind of ask you guys is, if I was going to have you drink this, but I was okay, we got it was safe. What's in it? So I tell you it's a sodium chloride solution. Just sodium chloride. Like,
no other living
so it's this water that I just water, right? What would you have to know? What do you think? What would you have to know about this before you say to yourself, how much salt, right? And how much, what else do you need to know about you? Yeah, what's safe, okay? And so, does anybody happen to know what the allowed percentage, what the allowed amount of stuff that's dissolved in water that they'll give to us through the pipes, or they say, your water's bad, we need to do something? Yeah, they're really starting to kind of push it out there because they're starting to want to pass bonds and measures and make us feel okay about recovering the water. Yeah, parts per million is good. We have devices to measure parts per million. Okay.